The gradient points in the steepest direction from where you're standing. And it's always going to be perpendicular to your level curves. Okay, each meets each level curve at a right angle, like that, when they intersect. One other thing is the actual magnitude, the length of the gradient. If I drag that gradient vector from the center closer to one of these edge parts, it's getting longer in some places, like right here, and then it's getting still kind of longer, and then eventually, in some places, it starts to shrink. What do you think the length of that Q-tip vector represents?
The steepness of the curve.
Yes. Once you get to right here, what tells you that this region right here is a relatively steep part of the curve? Well, not just a long gradient vector. I'm talking about the level curves. The level curves are close together for equal spaces of elevation. You have closer level curves right here, and then the closer you get to that peak, it kind of tapers off because you're not as steep as you get to the hilltop. So the length of the gradient vector plays a role in measuring the steepness at that particular place on the surface. So do you see why I call it a steepness compass? If this was a GPS map of where you're standing, and let's say you were standing right there, and you had this little gradient compass in your hand. Your gradient compass doesn't point north, it points in the steepest direction uphill from where you're standing. So if I'm standing right here, my steepness compass is pointing that way, perpendicular to the level curve I'm standing on. And it would also tell me the length of that vector. We can do the Pythagorean theorem on those components. I component squared plus j component squared to get the magnitude, but the magnitude of that vector would tell me essentially the slope at that point. If I were to walk in that direction, it's not really a partial derivative slope because it's both partial derivatives kind of combined together. It would tell you sort of essentially the change in z over the change in horizontal displacement. Not necessarily x or y, but you're kind of at a tilt. So your change in z elevation over your horizontal displacement there will be higher because you're at a steeper part of the curve. But then, if I drag that gradient vector closer to the hilltop, the magnitude starts to get smaller and smaller because the magnitude represents the steepness at those points. So, handy summary of information about the vector for gradient. Let me toggle back to the document camera. Okay. So again, I'll scan all this stuff in, the calculations for gradient and the information that I'm sharing with you. So, that's one of the important facts we've noticed about the gradient. The gradient is a vector which has the following properties. Are all of you familiar with the little inverted T symbol?
It's perpendicular.
Perpendicular to, or in some cases you can say normal. Normal is kind of synonymous with perpendicular. So it's going to be, the gradient vectors are perpendicular to the level curves of the function that it came from, the parent function. Do you know what that means? The magnitude of the gradient vector. In other words, you've got two components. Do the Pythagorean theorem on those two components. That's the magnitude, the length of the vector. The magnitude measures the steepness on f of xy. So, gradient's always, significant for its magnitude and its direction. So, the magnitude of the gradient vector, if I actually took the gradient for our function, plugged in, say, x equals 0, y equals 1, and I get a constant vector. That vector has a magnitude and a direction. The magnitude of that vector would be the steepness at that point going uphill. The direction is your steepest climb going uphill. Hey,
how you doing?
I'm multitasking. I can't write and speak at the same time. So, am I doing okay?
Sure.
Okay.
Absolutely.
Yeah.
Thank you very much.
So everything seems to be all right.
I don't know hardly any of these guys except for one.
I don't know about
Is this Calc3?
three. Is this Calc3?
Wow, they all avoided me for the whole time.
For the whole
Hurts a
thing.
little bit.
They've mentioned everyone.
Just checking in.
All right, you heading home? Take care.
Yeah.
All right. So those are the special facts about the gradient vector you want to sort of keep in mind as you're doing the problems. The homework that I've assigned, the first part of 14.5 is essentially things like this. You're given some multivariable functions and you're prompted to find the gradient. Some other things you might be asked to do. For the same function we've been looking at. Okay, evaluate the gradient. So I've already found the gradient. And this is looking more and more like a little shield than it should. It should be an inverted triangle. So sorry if it looks more like, 1940s Captain America shield. But evaluate this means to go to the gradient you created already and then plug in some values. It's kind of like function notation for inputs and outputs. And keep in mind the alphabetical order. This came from a function of x and y. So this is literally telling you to replace x with 1 and y with negative 1. So our gradient function we got a couple of, well, on the previous page was this guy right here. So if I evaluate that for x equals 1 and y equals negative 1, that's going to be, let me pull this up so I can actually do that. The e is going to be the same in both components. If I plug in 1 and negative 1, that's going to be e to the negative 2 for both of those. This will be negative 1 minus 2 times negative 1, so negative 1 plus 2. So that should be positive e to the negative 2. This component right here, again, that's going to be e to the negative 2 when the x and y get replaced. This will be 1 minus 2 times 1 times the square makes that become 1. So it's 1 minus 2, so it should be negative times e to the negative 2. So that's what I mean by evaluating your particular gradient vector. If we were still on that software package and we drug our cursor to the point as close as we could to the point 1 for x, negative 1 for y, it would give us an I component of this much, e to the negative 2. What's that? What? 1, 4? What? I got a calculator, I think.
0.135.
How's close? Okay, so 0.135-ish. So this is approximately 0.135 for I, comma, negative 0.135 for j. So let me toggle. I'm toggling. This is me. Toggle, toggle. So if I go to the point x equals 1, y equals negative 1, as best I can. Zoom out, actually. Oh, hello. There we go. There we go. Oh, no. That's not it. Surface plot. Oh, it can't do that with the gradient vectors right there. Poop. Okay. So go to x equals 1, and then y equals negative 1 as best as I can eyeball it. Let me see. I'm going to keep an eye on my coordinates up there. X equals. Wait. Yes. And y equals. Oh, shoot. Okay, it's close enough. I'm not going to try to do it. Close enough to 1, negative 1. Your I component, okay, almost 0.135. Your j component, close to 1 point, because I can't exactly get to 1, negative 1. So that's representing the individual components. The magnitude of this vector, well, again, if you did the Pythagorean theorem on those two components, it would tell you, standing from this point, walking in the steepest direction from where you are, and notice this is where the valley is. This is a valley part because all the gradient vectors are pointing away. If I walked in the steepest direction, the steepness at that point going in the direction of the gradient would be that squared plus that squared under a radical.
0.19.
So it's not pretty. It's 0.19-ish, yes. almost 1. Really? 0.19. you
Yeah,
said. It's almost 0.2. Okay.
Yes.
So essentially about 0.2 Z units for every horizontal unit. So 0.2, about 1/5. If I walked in the direction of this gradient this way, my Z elevation would change 1 unit for every 5 horizontal units I go that way. Not in the X or the Y direction, but in the direction of the gradient only. Okay? Kind of makes sense? A little bit? Okay. I'll hit the pause button when I finish. This is the pause button on section 14.5. You should have some idea how to get some gradient calculations done, but when you get to the problems that prompt you for directional derivatives, hit the brakes, because that's what we'll pick up with on Thursday. Okay? Any questions?
Can you upload your review with your notes on it as well?
My review.
When you wrote in like parametric and the section numbers
Oh.
all that in red.
Oh, you mean the one that I had scribbled on? Okay.
Yeah.
Because I had that there, but I didn't really do anything on it. I did a few problems here, just a few, like the concentric circles for level curves, and that is not your class, so where did that go from? So, I guess I can. Yeah, here it is. This is what you're talking about. This one right here. Yeah, so all I did was try to make a note of what section paired with what kind of, oh crap. I'm gonna do that a lot, embarrassingly so. So yeah, like this where I was trying to pair the sections with the, with their particular problem set. So I can do it, for this first page. I'll scan that in along with the few problems you asked me to double check and work over. And again, as you're going through the review, I've tried my best to answer these. I have not double checked my answers with Beth's because Beth didn't give me any answers, and again, she's not really replying to any emails. So I'm just sort of hoping, I believe I've answered them correctly. Don't get me wrong, I'm confident in my ability to do this stuff. I just like to, double check my answers versus hers just to see if, we got them both the same way. So I'll upload this. The answers to the review are on there. I just, didn't show my work. I just did my work on Scrap because that's a lot of typing to do. And so I did type up the solutions at least so they're somewhat legible. Okay, and I'll scan in tonight's notes. There'll be a new module. When you go to your D2L page under course content, you only have one module there right now, really, like, the first day stuff for the syllabus and then the few exam reviews that she's done. I'll put a new module that says Test 3 notes and review information because that's where I scan in all my stuff. And later on, I'll post old copies of stuff that I gave for Test 3. Now, my Test 3 is different, so I'll try to isolate where those topics are on some of my old tests so you can see what my problems were. Okay? Any questions? All right. Well, send me an email if you have any questions about preparation for Test 2. Test 2 will be in the testing center. Y'all know where the testing center is?
Mm-hmm.
Yeah.
ERC room 122, bottom floor, past the stairway, past the elevators, back on the left. Take a photo ID, ideally your student ID, so they can scan you in easily. But I've heard they will accept your driver's license, begrudgingly so, but they'll accept it. And the test will be in there tomorrow. Again, anybody want to try tomorrow? So I'll put the test in there beginning on Thursday. So I get an extra day to work, make it out and polish it up and copy it. Thursday, Friday, Saturday, and Monday will be its availability days. Okay?
Thank you again for that.
Hey, no problem. All right. I know you've been through, technically Test 2 is a month late. Because this class, Tuesday, Thursday classes got decimated.
Like most of that
Yeah.
stuff we didn't even, it was like a month ago.
Yeah. And so it's been spread out. It's time to do Test
Hard.
2. Let's stamp that, move on, and do the best we can with the time we have left.
We're planning on having class Thursday.
Oh yeah, we're having class Thursday. I'm not doing in class. The next time we'll have an in class test is Test 4 on final exam week.
And,